plane curves. Okay, that means suppose you consider a smooth map kappa from I to R2 is smooth map. Then there exists a unit speed plane curve alpha from I to R2 whose sign curvature will coincide with K. Signed curvature coincide with K. And not only that, the existence of such plane curve is unique up to a rigid motion. So the existence is unique up to a rigid motion. So let us have a look at the proof. Just I'm going to sketch the proof. So let us define. So let us define two functions, namely let us define a function phi from the interval I to R2 by means of this rule, that is phi of s will be integration s naught to s kappa u du. So that is, you are fixing this s naught. So I can, so let us fix s naught belongs to R. Okay, and another function, I'm sorry, this is not true. And another one is our desired curve, that is I to R2 by means of the rule alpha s is going to be integration s naught to s cosine of phi of u du, and another one is s naught to s sine of phi u d. Okay, so for all s belongs to I.
Excuse me, sir. Phi is I to R.
Yes.
The function phi.
Yes. One
And
minute. Yes. Yes, it is.
yes.
Yes, this integral is a real number. So
Okay.
alpha is a curve I to R2. Yeah. So okay. So this alpha is certainly be a parametric curve, and if you want to compute the first derivative, so what is that? So this is cos of phi s sine of phi s, right? I think so. This is the tangent vector of this curve, and since this is cos phi x phi s sine phi s, so certainly it is of unit speed. Okay. And not only that, this expression says that the unit vector alpha dash s making an angle phi s with the x-axis. So this makes an angle phi s with the x-axis. And therefore, by the above result that we have stated, it says that so your sine curvature will be, what is the sine curvature? Just taking the derivative of phi with respect to s. But what is that? By means of this definition, it would be k. Okay. So therefore, you have obtained a unit speed curve whose sine curvature coincides with this k, given k. Now we need to move forward for the uniqueness. So uniqueness of the existence of such unit speed curve. So that will be determined up to a rigid motion. So suppose you have another unit speed curve. So let phi bar s will be the angle between the x-axis and the unit tangent vector alpha bar dashed of another curve alpha bar, then you can easily get that. So this alpha bar dashed s will be, so since it is making an angle phi bar s with the x-axis, so it will be cos phi bar s. Yeah. Okay, at the point alpha bar s. And then by integrating, we will get alpha bar s will be integration. Suppose you are fixing a point s naught, then integration s naught to s cos of phi u du, integration s naught to s sine of phi u du plus some constant, which will be alpha bar of, there is a starting point. Okay. Now since phi bar is angle between the x-axis and the unit tangent vector of that curve alpha bar, then by the above theorem, you can say that the sine curvature K must be d phi bar ds. And from this equation, by integrating, you will get, so phi bar s must be integration s naught to s kappa u du plus the angle at s naught. Okay. So let us denote this phi bar s naught as theta naught. Okay. And alpha bar s naught as, suppose, a naught. Then just come back to this alpha bar s. You will get that alpha bar s will be integration s naught to s cos of, so what is your phi u? So it will be, yes, so it is phi u plus theta naught du, and s naught to s sine of phi u plus theta naught du plus the constant a naught. Okay. So here you have a translation T a naught of this point. Okay. Then after expanding this cosine and sine, so you will get something like this, that is T a naught of, you can think of a matrix cos theta sine theta cos theta, and a column vector. Integration of this should make a, so integration is not to s cos of phi u du, and another one is integration is not to s sine of phi u du, right? Okay. So this is a linear map preserving the norm. Okay. So therefore this is an orthogonal transformation. So you can take this as r theta, a rotation matrix. So T a naught compose r theta of this point, but it is, so this is your definition of alpha s. Okay, fine. So alpha s. So therefore, so this T a naught compose r theta. So this is a rigid motion. Okay. And this completes the proof. Okay. Now let us record some remarks. I think you have already computed the, I suppose this is one, I'm sorry. Yeah. So what is the suppose, okay, let us draw a circle, not 3. So suppose it is of unit radius. Then what is the curvature of this one? What is the curvature?
1.
This is 1. Okay. And again, yes, okay. And again, if you are going to take this example, suppose briefly you are just taking a helix, circular helix, that is alpha s is a cos s, a sin s, and bs, where a and b is half. Then what is the curvature of this? So this is your alpha, and suppose you can take this as gamma. Okay. So what is the curvature of this helix, circular helix? I've already given an exercise to compute the curvature and torsion of this curve. This is again 1. Okay, check. Okay, so these two examples, so say that their curvatures are same. Okay, but the curve alpha can't be obtained from gamma by applying any rigid motion. So whenever you are trying to enter into the space curves, so the curvature will not be sufficient to distinguish two curves. So by applying any rigid motion, so that is why you need to introduce another curvature which is called torsion. And then by fundamental theorem of space curves, curvature and torsion completely determine a space curve up to a rigid motion. Okay. Okay. Number 2. So suppose you have a regular plane curve having a curvature, having the curvature which is constant, positive constant. Okay. So let alpha be a regular plane curve whose curvature is a positive constant. Okay, then what will happen? Then the curve, the conclusion will be like that. So suppose suppose you consider the sine curvature of this alpha case, and this must be plus minus k, where k is your the constant curvature of that curve. Sorry. Okay. Now I would like to give a problem here, that one can check that the sine curvature is also a smooth function. Okay. Yeah. And so in particular, this will be a continuous map, and this says that the sine curvature will either be k for all points on the curve, or it will be minus k for all points of the curve, due to the fact that it satisfies intermediate value property. Okay. Now let us see that suppose you consider, suppose alpha a curve which is defined by small r cos of small s by r, smaller sine small s by r. So this is a circle centered at the origin with radius smaller. And if you compute, if you want to compute the first derivative, then what is that? What is the first derivative of this? So this will be making an angle pi by 2 plus small s by r. Because if you want to draw the picture, then it will be okay. So let us, so here, and this is your tangent. Okay. T. So this alpha dash dash is t, and it will be making an angle. So pi by 2 plus, so this is your small s by r. Okay. So therefore, making an angle pi by 2 plus small s by r with the positive x-axis. Okay. And therefore, it gives us the sine curvature of that alpha. So ks here will be, so dds of pi by 2 plus s by small r. That means it is 1 by r, right? Okay. So if your ks is greater than 0, then the circle of radius, the circle of radius 1 by ks will be having the sine curvature ks. And now if this is less than 0, then you need to take a reparameterization of the previous circle. That means you can take gamma bar s this way, the small r cos this one minus minus small r sine small s by r, and this reparameterization will have the sine curvature. So we'll have sine curvature minus 1 by r. That is, if the radius is minus 1 by ks, then we get a circle with sine curvature ks. So that is, if the circle is of radius minus 1 by ks, then it has its sine curvature as ks. And from the fundamental theorem of plane curves, so any curve whose sine curvature is ks can be obtained through a rigid motion to the above constructed circles. And notably, the rotations and translations obviously takes circles into circles. So it gives us the conclusion that any curve whose sine curvature is a constant must be a part of a circle. So alpha that we have considered before, so this must be a part of a circle. Okay. Number 3.
Sir, excuse
Although
me.
this is
Okay, alpha dash will be determined in terms of matrix, I think, 2 by 2 by Jacobian matrix.
alpha dash.
Alpha dash is.
So the alpha is a map from R to R2. So it must be a matrix of order
2 by
2
1.
cross 1.
2 by 2 plus 1.
Yes.
So it will be matrix, and that matrix will be making an angle on this.
Yes.
Okay, so we have to determine first alpha dash s.
Right.
Okay, sir.
Right.
Thank you.
Yes. Okay. Now, since a fundamental theorem for plane curves guarantees the existence of a plane curve with any given smooth function of pi s as its sine curvature, but sometimes, as we have witnessed for the case of space curves, that I have already given an example of twisted cubic from which you cannot express the parameter t in terms of its arc length. Okay, so in this case also, simple curvatures can lead to complicated curves. For example, if you take this example, this is also a familiar one. That is, suppose your sine curvature is simply s. Okay, for all s belongs to R. Then from the proof of fundamental theorem of plane curves, you will see that suppose you are starting from 0, suppose your s naught is 0, then first of all we have defined a phi s, and that is integration 0 to s. So it is t dt, something like this. So it would be half a square, right? And then your curve was defined in this way, that is integration 0 to s. So here you need to take cosine of half u square du, and here integration 0 to s sine of half u square du. Okay, so this is a spiral like curve, and the graph can be computed through through applying some numerical analysis applied to this integral, and it will be looking like this. I can also draw this one. Okay, so something like yeah, something like this. Yeah. So one cannot get any explicit expression of this one. So although fundamental theorem says that there exists a plane curve, but sometimes you cannot get any explicit expression at all. Okay. Okay. So now let us move to some interesting story about the local canonical form of curves, parameterized curves, and let us make some observation here. So what we have achieved so far is that whenever we are intending to study local properties of a curve around the neighborhood of a point, we have been equipped with a natural coordinate system, namely the finite triad at every point, and which will be referred to each time whenever we are dealing with the local behavior of the given curve, right? So you are getting some moving frames. Okay, and so now given any naturally parameterized curve, suppose alpha is of unit speed, and without having, because I'm going to define torsion, so without having singular points of order 1, and then you need to fix a point S0. Okay. Okay. And at S0, that means at the point alpha S0, you may consider a finite triad. That is, suppose T at S0, eta at S0, and B at S0. So which is a basis, orthonormal basis of R3. Now, without loss of generality, for the sake of convenience, we may take this S0 as 0, because we have already specified that you can take the translation, and the translation is a diffeomorphism. So you can take this S0 as 0. Then considering the Taylor's expansion around the neighborhood at 0, you must get, so by so you may get, so your alpha S will be alpha 0, small s alpha dash 0, half s square alpha double dash 0, and this will be 1 by 3 factors of 6, small s cube alpha triple dash 0, and okay, so let us denote some remainder r, where this r will be satisfying a property that whenever you are trying to make s tending to 0, then this expression will be 0. Okay. Note that since your S0 is 0, so this alpha dashed 0 is your t that has been considered here. Okay. And your alpha double dashed 0, so it will be by Serret-Frenet formulae. So it is your kappa eta, and certainly the alpha triple dash 0, it can be, so it is maybe you can compute it, and I can write this as kappa dashed eta minus square t plus tau b. Okay. Okay. Just computing the first derivative of kappa eta. Okay. Okay. So then, so therefore, so from this expansion you will get, so alpha s minus alpha 0, so it will be, yes, I just write down it as s minus kappa square s cube by 6 t plus s square kappa by 2 s cube kappa dashed by 6 eta plus s cube by 6 kappa tau b plus remainder r. So all the terms have been computed at the point 0. Okay. Okay. Now let us try to get into the very familiar situation, that is we are to consider the coordinate system, the standard coordinate system. That means this one is at 0, x-axis is y, and that means you are considering the coordinate system O x y z. Okay, and in such a way that the origin has been regarded as alpha 0, and with respect to this, your t moves to 1 0 0, your eta will be this, and your b turns out to be 0 0 1. Then for a point, suppose for any point at alpha s, that means its components are xs, ys, zs, then you can say that, so your xs will be small s minus kappa square s cube by 6 plus a component of that remainder r, the first component, and ys will be ys, what is ys? Yes, so half of kappa s square plus 1/6 of kappa dashed s cube plus ry, and your zs is 1/6 of kappa tau s cube. Rz. So where your r is this one, and this representation around the neighborhood of this 0, this is called the local canonical form of alpha around a neighborhood at 0. Okay. And now if you want to see the projections of the curve around the neighborhood of 0 to the planes, that means suppose you are considering, suppose your graph, so the trace of the graph, trace of the curve will be looking like this, suppose. Okay, so then this, so that means it is your t, eta, and b, right? And this is your origin. So you are projecting this curve around a small neighborhood of 0 of the origin, and you are trying to project it to the theta plane, TB plane, and eta B plane. Okay, so then the curve will be looking like, so suppose you are projecting to theta plane, then if you look at this curve, suppose you are projecting this curve to theta plane, that means this one, then so how does it look like? So something like this, right? From this one to this, yeah. Sorry. So this is your T actually, and this is your eta. Yeah. So this is a projection of the curve to the theta plane. Now I think you can project the curve to TB plane. Just try to make a projection, and it would be looking like this. So look at this curve. Now you are going to project it to TB plane, that means here. Then, so your that part will be here, right? And this has been projected into this TB plane. So this will be looking like this, that, right? Okay. And now just make it on your own. Project it to the eta B plane. Okay. Now let us make a comment here. So this will reveal that so why we have considered a negative sign.
Sir,
In the, yes. Yes.
sir, how can you say the projection of this like this? Is there any method or something like that? Just here.
Actually, for this case, actually, we are making some intuitions. So,
Okay,
and you
what's
can,
the intuition?
yes, yes, yeah, and you will get, okay, if you are trying to get this kind of situation, you can use the local canonical forms actually, yeah, for a particular term.
Actually, okay, if we use
Yeah.
the local canonical form, then we will get the T eta plane, eta TB plane, and eta B plane.
Yeah. Just we have just using the standard coordinate system, okay, through some. Yeah.
Okay,
So
so
this
it
is
will be
your standard coordinate system, and we have computed the local.
can it be done in tutorial?
And if okay, maybe, but it needs some time actually. So
Okay.
just take any familiar curve and compute it. I think it will be better.
Okay. Okay. Thank you, sir.
Okay. Okay. So note that if your, so let's suppose your tau is less than 0, and you're making your small s sufficiently small. Okay. Now then, if you look at the picture, then you will see that uh, in the theta plane that we have projected the curve here. So if so then your z in the local canonical form is z. So since your tau is negative, so this z decreases with s, correct? And the curve, so and the curve will cross, the curve will cross the osculating plane the curve will cross the osculating plane to the side, to the side opposite to which B is pointing, as Z0 is 0. So suppose you look at this one. Okay, I'm just trying to, that means I think so this is your, suppose this is your T, this is B, and this is eta. Okay. So as your, so you are making this s sufficiently small, and your tau is less than 0. So what is your z? Let me write it. So z is 1/6. So z is 1/6 kappa tau s cube plus rz. Okay. So now, so what is happening here? So therefore, the curve, so this curve here, and it will cross, so it will cross the osculating plane to the side, that means in this way, to which actually the picture is getting lost here. Let me just write down it. Yes. So this is your T, and certainly, yeah. So it will be cross the osculating plane, and just, I think, if you look at this picture, that will be better. Yes. So this is, so we are making this one. Yes. So as your S decreases, you are taking S sufficiently small. So this curve moves down to this one. So this goes. So if you look at this situation, actually, a very small neighborhood in this one. Okay. So your Z, so this decreases, and the situation is that, so it comes here, and then it crosses the osculating plane, and then go down here, and then go up. Okay. So this, okay. So therefore, it will cross the osculating plane to the side opposite to which B is pointing toward. Okay. So B is pointing toward this, and it will cross the osculating plane downward. Okay. And so that is the case of negative torsion. Okay. Now, for on the contrary, if you assume that for tau greater than 0, then Z increases with S, and the curve will cross the osculating plane at the initial situation, pointing towards the side to which B is pointing. Okay. And that will give you the situation for positive torsion. Okay. So for this reason, we have already assumed in the third equation of shaded finite formulae, we have take a negative sign, because if you start from a positive sign, then this situation will give you the reverse. Okay. So for that reason, in the third equation, we have assumed, we have put a negative sign there. Okay. Okay, so that's all for this discussion, and I think how much time I have.
Excuse me, sir.
Yes.
There can be infinitely many moving frames for a space curve. Is not it?
Yeah.
For any given point, there can be infinitely many unit tangents, infinitely many unit normals and binormals.
Can you repeat?
For any space curve, at a given point, there can be infinitely many unit tangents, and likewise infinitely many unit normals and binormals. So there can be infinitely many moving frames for a given curve. Is not it?
The voice is cracking actually. So
Okay, I'm
can you
typing.
write down in the chat?
Okay, I'm typing. Okay.
Okay, Suresh D. Okay.
उसको थोड़ा बोल दीजिएगा। Hello.
Hello.
Dr. Abhishek, can you throw some light on plane curve, because I think that was not discussed.
I have discussed about plane curve, fundamental theorem of plane curves.
Okay.
But you are talking about, I think, the level curve, right?
No.
That I have. So today I have discussed about plane curves
Okay.
and sign curvature of that one. It will determine completely the
So
geometric
you,
behavior, local geometric behavior of plane curve.
okay. Since we have around 15 minutes, if possible, you can take some queries from participants.
Okay, okay, sure.
So participants, you can ask some questions if you have any doubt.
Maybe there is a connection between there is a connection between level curves
Yes, yes, you can do.
and uh, and it and parameterization. Okay. So okay. So what does it mean by level curve? That I have already uh, defined in the first tutorial session. That suppose you have a map. Suppose you are in R2, and suppose you have a map from. If you can you give me 1 minute? Actually, someone is calling me.
Yes, yes.
Okay. Okay. So if you consider a function, suppose mm, from S to R, um, then we can think of a set. Suppose maybe some constant k. So this will be called a k level curve. Okay. For example, so the familiar situation like that. So this is a so here your function is okay, and this is a one level curve. And if you are going to take the function x square plus y square minus 1, then that is a zero level curve, right? That is fine. And like this, in R3, you need to take two functions. Suppose yeah, was R, and let us convene ourselves the domain of definition terms. And okay, so now can think of a set like that. So f x y z being okay, yeah. So f x y z maybe some k1 and g x y z. Okay. For example, so this is even a level curve, and in R2 you can define the level curve in this way, and you can extend this definition of level curve in Rn also. Okay. And for example, here, if you are considering two planes, suppose x, so these are your, these are known to you, a dash x, a dash y. Okay. So these two together will give you a video schedule, right? Enough. That is okay. Now we can talk of the parameterization of a level curve. Simply, you can say that a parameterization of a level curve is nothing but a parameterized curve whose image is contained in the level. So that is a very simple definition. That means we have already seen some examples. It is for suppose you are dealing with two-dimensional Euclidean space. So these are a family of equations. So you can consider this as a level curve by considering this. Okay. And then you can make a choice of parameterization. Here, as you all know, right? And okay, in that case, let us try to okay. So let me state a theorem. I think that will be giving some interest. That suppose that your function small f from D R2 to R, where D is an open set of R2, be a smooth map where D is open. And using this F, you can construct this set. Let C is your set of all points which will be satisfying this equation, right? Now, after assuming this, if some condition has been imposed, that means, so assume that now you can talk also, since you are considering a smooth map, so you can talk of partial derivatives. So assume that del f, del x, or del f, del y are not both 0 at, suppose, at every point of C. Okay, so you are assuming that either del f del x or del f del y is non-vanishing at every point of C. Now, if you just take a point in C, then you can assert that you can give a regular parameterization. I mean, there exists a regular parameterized curve alpha defined on an open interval I, and you can take that this I contains 0, so that uh, your alpha 0 is the point x naught y naught, and the trace of this curve is contained in C. So okay, so that means it is a regular parameterization of this given level curve. Okay. Now, if you would like to see the situation in this theorem, so what is that? Suppose so what does it tell actually? So suppose you have, so this is a very suppose you take a curve and this is your x naught y naught. Okay. And let del f del y not equal to 0 at x naught y naught. Okay. Then you can prove that since this map is smooth, so the vector del f del x del f del y at the point x naught y naught to the level curve C is orthogonal to the tangent at x naught y naught to the level curve C. Okay, so that means you can define this line, and this eta is actually orthogonal to this. Okay, so this is your x naught, and certainly this is your y naught. Okay. Okay. Now, since the condition says that suppose your del f del y is not equal to 0 at the point x naught y naught, so this says that actually eta it is not parallel to the x-axis, right? At x naught y naught, and which says that the tangent at C, that means, so this says that actually, so this implies, so the tangent at x naught y naught is not parallel to the y-axis, right? now if you are trying to draw the vertical lines around the neighborhood of x naught, now try to draw vertical lines. Suppose this is x naught minus delta, x naught plus delta. Now you are trying to I'm just deleting this tangent. So now you are trying to draw vertical lines. Then this line will intersect the level curve at this one. This line will intersect the curve at this one. this line will intersect the curve at this. So whenever you are considering a vertical line around a small neighborhood of x naught that will intersect the level curve C in a unique point, right? And the unique point, so this is also in some sort of small neighborhood of x naught, y naught. That means near to that point. So this intersects, so the vertical lines, in a neighborhood of x naught, will intersect the level curve C in a unique point, right? As it is evident from the picture also. Xy near x naught, y naught on the level curve C. So this says that actually, so basically you are getting a unique solution of this equation. Unique solution y in a neighborhood of y naught corresponding to every x, in a neighborhood of x naught. Okay. So this equation will have a unique solution, and so therefore, in view of the theorem, it says that actually you are getting a smooth function. You are getting a smooth function g from an interval something like this. Okay. So such that y equal to gx is a unique solution of the equation this, that is if x gx equal to 0 in y naught minus epsilon, y naught plus epsilon. Okay. And after getting this solution, you may consider a parameterization. What is that? So you may consider a parameterization. Suppose alpha, just taking from this to R2, as that alpha t is t comma gt. That is, your x is t and you have this y for all t belongs to this interval. And certainly, since your g is smooth, so you can compute the first derivative of alpha, and this, so suppose, so what is alpha dash t? This is 1 comma G dash T, right? So this reveals the fact that this alpha dash T will never be 0. That means alpha is a regular parameterized curve. Okay. Okay. So so assuming a level curve by considering a smooth map, so around some neighborhood of that point, you can be able to parameterize the level curve. Now one can prove the just state the result which permits you to pass on from a parameterized curve to level curve. Okay, that means suppose you are considering a, suppose it is a given a regular parameterized curve in R2 defined over an open interval I, and suppose you have fixed a point T naught, that means of the curve, then you can assert that there exists a smooth map capital F from that. Actually you are getting two real numbers, two positive real numbers, one is epsilon, another one is delta, through which you can construct a neighborhood of around x naught and a neighborhood of around y naught. Then there exists a, you can construct a smooth map F, which could be defined here to R such that del F del x and del x del F del y are not both 0 on the domain. Such that so with respect to this, so this will be a subset of the domain of alpha. So such that suppose we may denote it by J. So your alpha J, so that part of that parameterized curve will be contained in the level curve determined by this function. Okay. Okay. So this is the level curve. So you can try to prove this one. So with this one, I would like to finish my course.
Sir, excuse me. Okay.
Yes.
F to R, fx equal to x square plus y square equal to 1. This curve is of level 1 curve. And for the another example,
Yes.
if G subset of R3 to R and G R3 to R subset of D subset of R3, there are C is a curve AX plus BI. Is there any name of curve of level K level or something like that? K1, K2 level or?
If you are getting a you are getting same constant, then you can level this.
Actually, here two
Suppose
constants are there,
yes, yes, yes.
K1 and
That is
K2.
why I can't level for in general.
Yes, yes.
You can,
That's why you
yeah,
didn't mention the level. Okay, okay. Okay,
yes.
one thing, sir, I would like to, from when level curve to parameterized curve, when we are moving, and you have claimed that uh, why not, okay, the tangent x naught is not parallel to y-axis, and eta is not
Mhm.
parallel to x-axis. Actually, from the figure,
Mhm.
it is evident. But in there, another way to see or visualize that we can say it, or it is a
Mhm.
statement of the theorem.
No, no, no. Actually, the statement, yes, statement is
Statements demands it.
statement. Yes.
Eta is
Whenever you
not
are trying to
parallel to
prove
x-axis
this,
at x naught,
so
y naught.
this observation comes into the picture. Yes. Whenever
Okay.
you are trying to prove this,
Observations.
you are getting
Uh,
this.
okay, sir.
So I got okay. So whatever. So what will happen if the tangent to this level curve at x naught y naught is parallel to y axis?
Mm, exactly. Yes, yes.
If you are trying to, so I can pose a question. So what will happen if the tangent at x naught y naught is parallel to the y axis? If you can draw this, you will feel that what is happening here. Why you are imposing the condition that at least one of del f del x and del f del y must be non-zero at that time. Because at this situation, you are not getting a unique point. Maybe you can get more than 2 points, more than 1 point, and sometimes you will not get any point. The vertical lines will not intersect that point around a neighborhood. Obviously. Just try this.
Okay, thank you, sir.
Hello.
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 Hello. Yes.
Thank you, Dr. Abhishek.
Yes.
Thanks for sharing your video to the participants. So,
Thank you. Thank you.
once again, and thanking you for sparing your valuable time from your busy
So it
schedule
will
and
take 4 days.
sharing
Right?
your vast experience of the subject with our participants across the country. I am very
I
much
have
sure
tried. I
that,
have tried my best. I don't know how much.
yeah, yeah. So I am very much sure that participants have learned a lot from your lectures. And further, I hope that the fundamental ideas of curves discussed by you in these four lectures will form a good platform for forthcoming lectures on surfaces and smooth manifolds and further advanced topics which are going to be discussed in third week. So finally, on behalf of Department of Mathematics and Statistics, Central University of Punjab, and as a head of the department, and also as a convener of this summer school, uh, I am very much thankful to you for your time and these fruitful discussions. So
Thanks to all
thank you,
for this
thank you,
opportunity.
Doctor.
Thank you.
So you will be there in tutorials also or not?
I think Somo will take care of that as he has told
Okay,
me.
okay, no problem.
Yeah.
Okay, thank you. So now we will conclude this session, and next lecture will be by Dr. Vikram at 2 p.m. So please join on time. So thank you.
Thank you.